So, this is Chapter 5, and it's Section 7. And there's 2 topics for today. Okay? And these will be tested on the final exam. They will not be tested on our exam next Wednesday. Okay? So, we're going to cover what's called implicit differentiation. And then we're going to do some related rates problems. And actually, these are 2 very nice topics that definitely belong in Applied Calc 1, not Applied Calc 2. By the way, how many people are planning on taking Applied Calc 2? Just show of hands. How many people, this is it, you fulfilled the requirement? How about finite math? So a number of people. How about statistics? Okay.
I fulfilled it.
I mean, just a quick aside. But this topic, like I said, belongs in Applied Calc 1. There's no doubt about it. It's talking about taking the derivative. Both of these are. And it's yet another application. Okay. So the idea is this. If I write this equation down, x squared plus y squared equals 9. Now I'm really tapping into your algebra. If I say graph that equation, do you know what that equation represents? Let me change the 9, guys. I don't like that 9 so much. Let me change it to a 25. So I guess what I want to do is I want to plot some points that satisfy that equation. I need an x value and a y value that works. Right? Can you give me an x value? Okay, 5. But then what do you have to put in for y to get the equation to work? 0. So there's a point, 5, 0. Actually, once Matt shouts that one out, then others of you are going to come up with another idea. What else could I put? 0, 5, Mike says right away. What else could I put? There's going to be other ideas that this sparks. Negative 5, right? Because why would that work? Well, we're squaring it, right? And so someone's going to shout 0, negative 5. So far, there's 4 solutions to this equation. Are there more? We did 0, negative 5. There, 3 and 4. Is that true? 3 and 4. Mike came up with 3. What's 3 squared? And what's 4 squared? 9 plus 16, 25, right? So, I don't know, somewhere around here, I guess, would be 3, 4, maybe right there. And then somewhere over here, someone's going to come up with 4, 3. Anyways, if you were to graph all of these, you may remember from some long ago algebra class that if this is in the form I think it is, which is x squared plus y squared equals r squared, right? That's a circle. What's the radius of the circle? 5, right? That's why it goes out to 5, 0. So there's a nice little picture of a circle. Now, circles have tangent lines. True or false? Sure. Think of a baseball hitting a bat, right? They have lots of tangent lines. A circle is a function, true or false. Doesn't meet which test? Now, the vertical line test, right? To be a function, we don't meet that. So that's a problem. If we want to do calculus, so far, we've only been able to take derivatives when we have functions. Okay? Well, the idea of implicit differentiation, what the idea is, this allows me to take, or let's say to find derivatives even if I do not have a function. Okay? And you might say, well, why do I need that? Well, let's zoom out a little bit and give you a little better view. You know, like I said, we have tangent lines here. Matter of fact, here's the point 4 comma 3. There's a tangent line there. And, you know, here's one of our classic problems we've been doing all semester. Find an equation of the line tangent to this circle at the point 4 comma 3. Well, you already know part of the answer. You know that we use the point slope form, and we're going to go y minus what? Yeah, 3, because that's my y1, is equal to m times x minus 4. The only thing you don't know is the slope. And normally, what would I do to find the slope? What would you do normally? You'd find the derivative, and then there'd be one more step. The derivative, you'd have some function of x, right? But then what would you have to do next? Okay, you use the 4, right? You substitute in the 4. So, I'd still like to be able to take a derivative of this x squared plus y squared equals 25. And so I do. I just do. When you do this implicit differentiation, and actually related rates, both of these use what's called the chain rule. And by now, we're getting more and more comfortable with the chain rule. At first, that was tough. Right before exam 1, right? That's when we were studying the chain rule. But I think we're getting better at it. That's one of the ways we've grown. So here I go. I have my equation. X squared plus y squared equals 25. And what I'm going to be doing here are demonstrating steps, I guess. What I'm going to do is I'm going to take, when I write this, do you know what that means? Derivative with respect to x of both sides. Okay? I'll do the right-hand side. Thanks, Paul. Okay? Now we're going to work through the left-hand side together. Of course, the derivative of x squared is, because it's bing, bing, and then really, what's the chain rule tell me? You take the derivative of what's inside, but what's the derivative of x with respect to x? It's just 1, right? And we don't even write that usually. But because I want to emphasize the chain rule, I'm going to write it. Plus, and maybe that'll explain what happens next. When I take the derivative of y squared, this is a little bit interesting. See, y is usually a function of what? Now, I understand in the picture y is not a function of x. We don't have a vertical line test. I understand that. But I'm telling you that by the green tangent line there, if I just kind of zoomed in, isn't it true that y does look like a function of x right around there? If you just zoom in that window, you would meet the vertical line test. So we get away with it. We get away with treating y as a function of x. And because it is, I can take its derivative with respect to x. And so I get 2 y, that's bing bing. And then here's what usually students find confusing at first, but maybe you'll get it. Times, I'm going to write dy dx. That's the chain rule. Bong. Because what's inside is y. That's what we're taking the derivative of for the chain rule. Now again, y is some function of x locally. I don't really know what it is. But remember, in order to find the slope, what I really want is dy dx, okay? So I guess my next step is I'm going to try to isolate dy dx. So let me do that. I get 2y dy dx is equal to negative 2x. And so I get dy dx is negative 2x divided by 2y. Or if you want, you can just write it as negative x over y. See, that's a formula. Now, to find the slope we want, okay, my slope m, I can use that formula. But notice this formula is different. It has an x and a y in it. You see that? What do you plug in for x? 4. What do we plug in for y? 3, because we said we're at the point 4 comma 3. So what's the slope? Negative 4/3. So what's an equation of that tangent line? Well, it would be y minus 3 equals negative 4/3 of x minus 4. We did it. We found an equation. I think I'll simplify it just to make it a little easier to understand. So this is plus 16/3 if I do 4/3 times 4. And then if I add 9 more thirds, because I'm adding 3 to both sides, what I get is, bless you, y equals negative 4/3 x plus 25/3. Now, how high is 25/3? A little more than what? A little more than 8, right? Because 24/3 would be 8. And if you go back up and take a look at the picture of the tangent line, if I were to trace it out, oh yeah, it would hit the x-axis a little bit above 8. Okay, so. But that's an example of implicit differentiation. You guys follow? Questions? So I'm going to give you some problems from your book now. And these are slightly more complicated, but I wanted to start with a basic one and then go from there. So I want to show you, you can work with, now we'll be able to find derivatives of almost anything you could think of. It doesn't have to be a circle. It doesn't have to be a function. And I like problem 18 as an example because this demonstrates a lot of things we've done in calculus. So we have xy plus y squared equals 4. Now your graphing calculator won't graph this thing because it's not a function. If you type it in the internet, you could probably find out what the graph looks like. It's a parabola tipped sideways. Same idea. I want to find a tangent line, I'd have to find dy dx. So again, the first step I'm going to do is I'm going to take d dx of both sides. All right? Ooh, we got to be careful here. When you do d dx of the very first piece, the very first term, see how it says xy? Think of that as a uv. What rule am I going to have to do here? Product rule. I'm going to need u prime v plus uv prime, right? So what do you think I'm going to write? What's u prime? 1 times y plus x times what? Not 1. Right. That's kind of the tricky part, I guess, is anytime you take d dx of y, that's dy dx. Next, we're going to take the derivative of the y squared now, right? this piece here. So we're going to write plus, do you know what to put? It's going to be 2y dy dx. And then equals, well, it'd be 0, right? Because the derivative of 4 is 0. So this example is a little tougher because, do you see how there's more than one dy dx? So there's some intermediate steps. So what I'm going to do is get all the dy dx terms on one side. Other stuff, move to the other side. Okay. So if I do that, I have x dy dx plus 2y dy dx. But I want to move that y over to the other side, so it becomes negative y. Okay, next. I'm going to factor out dy dx. You see, if you do this, if you put everything else on the other side, then you can take dy dx out as a common factor. And what would I be left with then? I'd be left with x plus 2y. So then the final little bit here, dy dx equals, well, I guess what I'd get is negative y over x plus 2y. And that's a formula with x's and y's that, again, you could use if you wanted. Guys have questions on this? So far, so good? Okay. So we're going to have to do an application with this for sure in a minute. Let me find one here. All right, so an application of this implicit differentiation.
And what about 22?
22?
Yeah,
You want to see 22 as an example?
sure.
Okay.
We'll do that after 64.
Let's do 22 now, because I have room and because you asked, and then we'll jump to 64. So 22, we have y plus 3 squared equals x squared minus 5. That's a good example. I guess what I would do is I would follow the same steps, but I would slow down a little bit. What's the first step, guys? d dx of both sides. And again, the right-hand side, that's no problem, right? What's the right-hand side? 2x plus 0, right? Because the derivative of negative 5 is 0. I don't need to write that. It's the left-hand side that can be confusing. So let me go through slowly. What's the first thing I write down? Bing! Put down the 2. What's the next thing? Bing! Y plus 3 to the first power. And then, bong, I need to take the derivative with respect to x of y plus 3. Good. It's just dy dx. That's right. So I have 2 times y plus 3 because you get dy dx and you also get 0. Okay, so all this equals 2x. And so now dy dx, what would it be? 2 times y plus 3, and you could simplify that, and it would be just x over y plus 3. The 2's cancel because everything's being multiplied. Does that help?
Yeah.
Okay. Yeah. So 64 couple things going on here. The function they give me says x squared equals 1,000 minus p squared. So obviously I'm using p instead of what? Okay. And we've done that before. What we have here is a price-demand equation, not a function anymore, right? I mean, could I get p by itself here? You could, but what would you have to do eventually? You'd have to take the square root and put plus or minus, and it wouldn't be a function. You have to treat the cases separately. A lot of times it's easier just to do part A. They say use implicit differentiation to find, well, dp dx. You guys ought to be able to do that. Why don't I go ahead and pause and let you guys do that? And then if you want to try part B, go right ahead. All right. So again, I take d dx of both sides. Okay. So on the left-hand side, I just get 2x, I guess times 1, but I'm not going to write that down, equals, well, 0, minus, and then let's see if you got it, 2p, and then also what? dp dx, okay? So that's what you need is dp dx. And so dp dx is equal to, it's negative 2x, oh no, it's positive 2x over negative 2p. And so yeah, I would say dp dx is equal to negative x over p would be one way to write it. Okay? And so now part B, well, that's kind of like me asking you, you know, if I give you this or if I give you this, are those the same?
Well, I'm asking if they, it doesn't seem like they're the same based on part B though.
Okay, so,
That's why I'm making sure.
okay, it won't matter
Okay.
in the same way this doesn't matter. Both of these fractions, of course, are equal to negative 3/2, negative 1.5, right? But I could see where you're saying, wait a minute, what's going on here? So let's go ahead and try and interpret part B. Part B, first of all, yeah, what does it say? It says, evaluate and interpret. And then how do you read that? Well, I would read it as dv dx evaluated, I'm sorry, not dv, dp dx evaluated at the point 18, 26. Now I guess you have to know what's what. Yeah, you got it? I mean, normally our points are written x comma y. I'm going to presume something here that this is written as x comma p, right? Because p is the function of x. It says dp dx. So I'm assuming that's what we have. Okay? So first thing you do is you evaluate it. Well, find the value. dp dx, find the value, evaluate. So I need to do negative x, so that means I'm going to do negative 18, right, over p, over 26. And so that's, well, it's a fraction. I just use a calculator real quick. Let me do 18 over 26. .6923. So negative 0.6923. Now we also need units, right? And I didn't, really say much about that yet. So if I go back up to the original problem, a couple things they told me. They told me that 10 is less than or equal to x is less than or equal to 30. That's the reasonable domain for this model. they tell me that X is the demand for their silk ties in thousands. So what I'm reading here is that the demand is somewhere between 10,000 and 30,000 what? Silk ties. And P is the price. By the way, we don't have the price function, do we? We may not know it. Maybe all we know from the economists is that there's this relationship. But I can go ahead and I can then use it. So if there's between 10,000 and 30,000 ties, what does this tell me now? I computed dpdx. What are the units? I guess that's it. P, we know, is the price. So this is dollars per 1,000 ties. All right. I gave you the units, and I want you to talk to someone near you and see if you can interpret it based on the units that I gave you. Go ahead and talk for a second. Let's see if you can make sense of that. So I guess I'm going to say a few things here, okay? I'm going to try to write it out the way I would want it written out. So when the production level is at, and what should I say? 18,000 ties. There's a couple things I can say. First of all, just the fact that I have an 1826 here, okay, I'm going to say, and really maybe it should be the sales level, I don't know. But the price, so let's say sales level. The price will be, well, $26. But now I'll interpret what we just computed, okay?
And it is decreasing.
It's decreasing if I do what? Yeah, that's right. And each increase in the production level or I said production again. What should I say? Sales level, let's say. Of 1,000 ties corresponds to a drop in price by, well, only 69 cents. I have a question for you guys.
Can you?
Oh, yeah. So, again, increase in the sales level of 1,000 ties corresponds to a drop in price by 69 cents. You drop the price less than $1, and you'll sell 1,000 ties more. If you drop the price about $7 or $6.90, you're going to sell $7,000, 7,000 more ties. I guess I have a question for you guys. Do you think we should drop the price? Okay. I'm hearing yes, and I'm hearing depends. What does it depend on, John? It does depend on profit. I'm selling them for 26 bucks. What do you think the cost is on these silk ties? 10 bucks? Well, then we're doing pretty well on markup, aren't we? I mean, these are questions that obviously, if you want to answer, you need more. Matter of fact, the kind of stuff you guys did for homework last night with the elasticity, that could help me answer whether or not to raise or lower the price, right? But this is just, you know, another example of computing a derivative and explaining what it means. It's a rate of change. And again, my thing is, when I look at a derivative, I want to write the units, dp dx, that's dollars and that's 1,000 ties. And that'll help you put together an interpretation. Okay? So I think that's the way to proceed. Do you guys have questions on this one before I do something else? Okay, so related rates. Same idea in terms of the mathematics that you're doing. What we're going to have is we're going to have two different functions of t, where t stands for what? Time. Okay. I'm going to give you guys an example here. This is problem 56 from your book. We have x squared plus 9y squared equals 18. By the way, do you guys know what the graph of this one looks like from your college algebra days? I'll give you a hint. It's not a circle. It's an ellipse. Yeah. This 9 here means it's not a circle. And back in the day, you probably had to divide by 18 to figure out what kind of ellipse it was. This one, you had a fot or a fog. I don't know if you did that. There's a football on the tee or on the ground. There's a football on the tee. So is that kind of an ellipse? Okay. Thanks. So that's an ellipse. Now, this ellipse, again, is not a function. By the way, where's the first place you ever heard about an ellipse? Me too. It was not math class. It was science class. I was in like first grade, and they taught me that. What did they teach you? The orbit of the planets. Yeah. But honestly, you know, the orbit of the planets, they're ellipse that looks like about like that. I mean, they're almost circles. I mean, they're so close to it's very funny that they even bother to teach it to some little kid, because if you look at that and say, what shape is it? They're going to say circle. Right? So anyways, yeah, the planets don't, only Pluto looks like this, and now they don't even call it a planet anymore, right? They changed it on me. Poor Pluto. All right, so anyways, but the reason I bring up planets is because, think about the planets moving in an ellipse, right? You know, if I'm right here, or if I'm up here, the planet is moving, say, in an orbit, right? Isn't it true that x is changing and y is changing as the planet moves? It is, right? X is changing and y is changing both. And so, I guess my question is, can we find an expression to tell me how x is changing and how y is changing? So now, they give me a few details. They say, the problem 56 asks me to do the following. It says, find dx dt. That's what I'm supposed to do. Find how x is changing with respect to time. And they tell me a few more things. They tell me when, and they give me some details. They say x equals 3, they say y equals 1, and they say dy dt equals 10. Did I make that mistake? I sure did. Yeah, if I divide by 18, this is my picture then. It's an ellipse, but it's the wrong way, guys. The picture's this. That's better. Okay, so here's the origin, 0, 0. And so let me draw a few things, guys. dy dt is 10. That's hard to draw. Let me draw this first. X equals 3 and y equals 1. So right over here is my planet, 3, 1. Now the other thing they told me is that dy dt equals 10. And I drew it as an arrow going up because that's the y direction and it's positive. Hey, by the way, let me ask you guys. If that's true, if the y direction is going to be going up, where do you think the x direction is going to be going? Well, it's got to go left or right. And I guess my question is, which one? I don't know. I guess we'll see. We're going to work it out and see. It has to stay on the orbit, though, right? So if you think of this as like a bead on a string, and if you pushed the bead upward, it wouldn't slide upward because it would stay on the string, but where would it slide? Wouldn't it slide to the left? We'll see. All right, so here's how this works. The idea for implicit differentiation, we want to take not d dx of both sides, d dt of both sides, to get what's called the related rates equation. All right. Taking d dt of both sides. So watch what happens. There's the original equation. Again, I'll do the right-hand side for us. That's 0, right? But the left-hand side, well, what's the derivative of x squared? It's 2x, but now I'm going to do something I didn't do last time. I'm not just going to put a 1. I'm going to write dx dt. I'm thinking of x as a function of time. Plus, I have a 9, 2y dy dt. Again, it's very much like the implicit differentiation, but you're differentiating with respect to t. And so this is what's called the related rates equation. Again, it's 2x dx dt plus 18y dy dt equals 0. Now I heard you say factor out. In those implicit differentiation problems, that was the next step. But do you guys notice? I have dx dt and I have dy dt. I can't factor out. Those are different. I guess I could factor out a 2, but I'm not going to. All right? But what I am given, I was given a few things. I was given, up above, that dy dt is equal to 10. So down here where it says dy dt, I'm going to put a 10. Was I given the y value? We were, right? What's the y value? 1. And the only other thing I was given was the x value is 3. Matter of fact, if you look at it, the only thing I was not given was dx dt. And that's how you're able to solve for it. Okay? So I'm going to take that equation and I'm going to solve that for dx dt. I'll just move it over here. So I have 6 dx dt plus 180 is equal to 0. So 6 times dx dt is equal to minus 180. And so that means that dx dt is equal to negative 30. Now, I don't expect that we have all that many astronomers in here, but I am going to represent what that means on my picture. When I say dx dt is negative 30, that means as time goes by, the x is moving which way, right or left? Now you know it's moving left. It's negative. And I claim it would be doing 3 times as much in that direction, right? If that's 10, then here's what I just learned. dx dt is negative 30. And you can kind of see that from the path it would take on the ellipse, that it's going to move faster left than it will up. It only has a little bit more to go in the upward direction, and then it starts coming back down. You guys see that? So I think that's a nice way to visualize related rates. And I just thought we'd do one more application of it, and then we'll about to call it quits. So let's see. If you turn the page to it's number 78, there's another price demand one. I thought that'd be a nice one to kind of close up shop with here. Page 400. Okay. So I have a price demand function. P equals 40,000 divided by x to the 1.5 power. Okay. And it says x is demand for oranges in bushels per month. And then the P is the wholesale price per bushel. It says the local farmers market finds that the demand is currently 900 bushels each month. Well, by the way, what did they just tell me? So I'm kind of given a few things. What's that 900? That's my x. X equals 900, right? What else am I given? Let's see. It's increasing at a rate of 100 bushels per month. What's increasing? The demand is increasing. So how would I write that? As time goes by, dx dt is increasing, so we want positive 100. Okay? You just over 1, right? 100. 100 bushels per month. So I'm given x, I'm given dx dt. Ooh, you know what I wasn't given? Yeah, I wasn't given y, or I wasn't given a price, right? Can we compute the price? We're going to need that. Okay, you'll see in a minute, actually. Well, actually, maybe not. All right, so anyways, the question says, how fast is the price changing? They didn't ask you what the price is. That's interesting. They just say, how fast is the price changing? What they're really asking you in the world of mathematics is find what? dp dt. That's right. That's what they're really saying. Find dp dt. So that's not hard. I guess I would just write down P equals 40,000. How about we write it as x to the negative 1.5? And then what am I going to do to both sides? Take the derivative. Which derivative? D what? Take d dt of both sides. Let's see what I get. Well, the left-hand side ends up being very easy here. It's just dp dt, which is what I'm looking for. And then the right-hand side, let's see. Well, I have 40,000. And this is x to the negative 1.5, so let me bring down the negative 1.5. And then it would be x to the negative 2.5. Sure, subtract 1. So we can work out what that is. dp dt. I'm going to try and simplify that for you. What's that? Oh, yeah, I forgot something. Thank you. Bing, bing, what'd I forget? Bong. I'm taking d dt of both sides. Way to demonstrate it, Paul. dx dt. Bing, bing, bong.
We already know the answer for DXDT.
Yeah, we know those things, right? So let's see what we have. We have 40,000. We have negative 1.5. We know x, what they tell me, 900. So I need 900 to the negative 2.5. And now we know dx dt at that instant is 100. So I fill in the things I know, and I'll just use my calculator and be all done. All right, so let's see what we have. Clear this first. We have 40,000 times negative 1.5 times, now I have 900. I'll hit the caret key for my exponent, and I have negative 2.5, and then times 100. So it says negative 0.2469 0.2469. So let's come up with how we interpret that. And again, it really has to do with units. T, what is dt? That's change in time, but what are the units? Oh, you're doing P. So P is price per bushel. What about T? Time is measured how? So per month. Okay? So now let's see if we can interpret what we just read. Well, I would say when the demand is 900 bushels per month, and when the wholesale price per bushel no, we didn't have that, did we? We didn't have P. We don't know that. Scrap that. We weren't given that. When the demand is 900 bushels per month and is increasing $100 bushels per month, we will have, yep. So when the demand is 900 bushels per month, because they gave me X is 900, and we had dx dt is 100, we will see a decrease in the wholesale price per month, well, per bushel, the wholesale price per bushel by about, let's say, 25 cents per month.
Could you put that down?
Per bushel per month. Yeah. Okay. So the price is given in price per bushel, and then yeah, we see that. It's a month also. Is it again? No, I got time. Good. I'm glad. All right, so I guess the last question is, do you guys have homework questions from last night? That's what I'm looking at. Okay, so here we have section 5.6, number 45. Elasticity.